CE Tech Nest. In this lecture, we'll be discussing few more problems in continuation to the previous lecture. So let's begin. So the question is y is equal to d plus a plus b in parenthesis the whole bar. When we apply De Morgan's law, it will be split into d bar into a plus b the whole bar. Further, we have to apply De Morgan's law to this component, and after that we'll get the value to be a bar dot b bar. When the operation in the equation is plus, after applying De Morgan's law we'll get the operation to be and or dot operation, and finally the reduced expression will be d bar dot a bar dot b bar. Next you have to write the logic gate representation of the given expression. After that you have to represent it in terms of the NMOS and PMOS. First, as we have parenthesis here, initially A and B will be in parallel with each other, and further the parallel combination is further connected to the D. D is a single and it's not in parallel with either A or either B. It is both the combination of A and B further in parallel with the D. Similarly, in order to draw the PMOS circuit, you have to consider the complementary, and here you have to consider D in series with A and in series with B. So this is how you represent it. Next, you can consider any one of the example and uh, take it as an example, and then you can tell the examiner or whatever you're writing what happens to the PMOS and NMOS in each case based on the inputs that you give. You can write these sentences, you can pause the video and note down if you want. Next is this is already discussed, that is the AOI gate combination. In some questions they will directly ask to write the design of an AOI gate. In that case you have to write the boolean expression to be AB plus CD the whole bar, and then continue with the procedure. This I have already explained in the previous lecture. And next we'll further move on to the other problems or the next concept. So the next concept here is pass transistor. Pass transistors are also a type of transistors and it can be used as switches. So here we'll look into the pass transistor. This is the NMOS transistor where we have three terminals, that is the gate, drain and source. And the gate is the control input and we get output at the drain terminal. Source is also the input but the control is in the hand of gate terminal. Similarly, in the PMOS transistor also we have three terminals, gate, drain and source. The output is taken at the drain terminal, and NMOS transistor works for G is equal to 1 and PMOS transistor works for G is equal to 0. So now we'll look into each case what happens when the G value is 0 or 1. So NMOS produces strong 0 because it's connected to the ground, and here PMOS produces strong 1 because it's connected to the VDD or VCC. Next we'll look into various conditions or cases. So here I have given G is equal to 0. When G is equal to 0 is supplied to the NMOS transistor, it will be in off state, and similarly when G is equal to 0 is given to the PMOS transistor, it will be in the on state. Next, when the G terminal is given an input 1, the output will be in on state, that is the close switch. Next, when the value of G is equal to 1, the PMOS will be in off state or an open switch. Now we'll look into based on the strong 0 or degraded 1 or degraded 0 and strong 1. Here you can see when G is equal to 1, we'll get the output as 0. and hence we represent it as strong 0 because we are getting the entire value of 0 and not the approximate value. Next, when we give G is equal to 0 to the PMOS transistor, we'll get degraded 0, which means the entire output is not obtained and partial output is obtained. Therefore, we are approximating it to be degraded 0. And next is when G is equal to 1, we'll get degraded 1 in case of NMOS because it's not the complete value of 1 that we are getting, it's only the approximate value. And similarly, when we give G is equal to 0, it is the strong one, that is entire VDD is getting we'll get at the output. So this is how you represent a pass transistor. So this is NMOS without a bubble and this is PMOS transistor. Together combines to form the pass transistor, or it is also called as the transistor gate. So now we'll look into the truth table. When G is equal to 0 and A is equal to 0, the PMOS will turn on and NMOS will turn off, and the output obtained is degraded 0. Next, when the input G is equal to 0 and A is equal to 1, PMOS will turn on and NMOS will turn off, and we get strong 1. When G is equal to 1 and A is equal to 0, PMOS will turn off and NMOS will turn on. We'll get strong 0. Next, when both the inputs G and A are 1, NMOS will turn on and PMOS will turn off, and hence we get the degraded 1. So these are various transmission gate or transistor gate symbols. You can represent the pass transistors like this also by representing it in the form of a square or like this, or inside a circle with a cross mark, and it has 4 terminals. So the probable question asked in this topic would be design a MUX using CMOS. So first we'll consider the 2:1 multiplexer. Here we have one select line and 2 inputs D0 and D1 and one output Y. So when the select line is 0, and then D1, there is no input at D1 and D0 is 0, we'll get output at Y as 0. And when input at the select line is 0 and D1 is in high impedance state or no input, then we get D0 as 1. So hence the output will be Y is equal to 1. Similarly, when the select line is 1, it will depend on the value of D1. When the select line is 0, it will depend on the value of D0. And whatever value is present in the D1 or D0, it will be produced at the output. So final expression will be Y is equal to S into D1, as when S is equal to 1, D1 is considered, and S bar into D0. S bar represents when the select line is 0, D0 is selected. Next, this is how you represent the 2:1 multiplexer. This is the CMOS block, and here we have two CMOS block, one for select line as 1 and another for select line as 0, and then you connect it and you get the output. Next one is similarly you can write like this. As previously I have shown the symbols of transistor gates. You can represent in any one of the form. These are different forms in which the 2:1 MUX can be represented using transmission gate. So here you can see these are the questions in the PYQs. Design a 4:1 MUX using transmission gates, and also the other question would be design of a memory element, that is the D latch. So now we'll discuss about the D latch. Latch is a level triggered device, and you can see here we are designing the D latch. It has one clock and D is the input and Q is the output. So latch is level triggered. Now in D latch it is also called as data latch, which means whatever is the input, it's obtained at the output. So here we have the multiplexer. To the multiplexer we have inverter gate, and again we have connected another inverter gate. If we take output here, we'll get the complemented output. If we take the output before the inverter gate, we'll get the normal output. And feedback is given so that the same value reaches the output as that of the Q value. Here we have used another NOT gate because the Q bar input is given to this NOT gate, and finally we'll get the value Q. So this is how you represent the D latch. This is the waveform that you get after each clock cycle. So next question we'll be discussing about is 4:1 mux. Similar to 2:1 mux, you have to write the symbol as well as the truth table. After that you have to write the final boolean expression that you get. And here instead of 2 blocks of CMOS, you are using 4 blocks. One for as we have 2 select lines, there will be 4 combinations, that is S0, S0 bar and S1, S1 bar. So this is how you represent it. Finally you have to get one output, therefore we have used here 2 select lines. So the next concept is we'll discuss in the next lecture. Thank you.